Hello and welcome to the TCIPG monthly webinar for the month of April. And spring will come around here sometime, but we're still waiting. We're about a month late. Today we are pleased and honored to have Jeff Gooding from Southern California Edison. Jeff is the IT program manager, general manager for smart grid system engineering with Southern California Edison, and has a broad scope of responsibilities in that capacity. But Jeff is known to many of us as one of the thought leaders in issues related to cyber, smart grid, and cybersecurity and smart grid. So we're very lucky to have him today. Before his present position, he oversaw the deployment of Southern California Edison's advanced metering infrastructure, which I understand was 5 million meters. And he's been with Southern California Edison for a little over 10 years, and before that, various consulting capacities. Today's talk, according to the abstract, is going to be trying to draw some lessons learned from when Department of Defense and those organizations went to network defense. And so, as I put it, smart grid cybersecurity is like IT cybersecurity, except when it's not. And Jeff's going to clear that question up for us. Thank you.
Great, thanks a lot, Al. So today I'm going to walk you through, Southern California Edison's approach to securing the electric grid, and it's part architecture talk. How we sort of figured out what architectures would work and what wouldn't, and part cybersecurity on some of the very specific work that we've been doing to secure the electric grid for the past 5 years. Before we get to that, I do want to give you guys a brief overview for those of you that aren't familiar with Southern California Edison. So we're a large investor-owned utility in Southern California. We serve about 14 million people, over 50,000 square miles. As Al said, we have 5 million smart meters currently deployed, and you can see the rest of the stats on the screen. Some other stats that aren't here that are of interest during the talk: we do have about 1,000 substations, about 200 bulk electric substations that are under NERC jurisdiction, and those are considerations as we work through designs to secure the electric grid. So I think this is the same everywhere, but to me in California it feels like we're first up because some of the progressive policies on sustainable energy and renewable adoption in California tend to be first in the country. But a lot of other states across the country and across the world have similar progressive types of goals. So if you look at what's happening to the grid today, the grid is stable largely because, the same way it has always been over the past 100 years, largely because there's bulk generation that has large spinning mass, which propagates a robust waveform all the way from central generation down to the customer. And this robust waveform allows the electric grid to ride through a lot of transient events and largely remain stable. As we take this inertia, as it's called, out of the system and replace it with wind power, solar power, even introduce power electronics in certain places that takes inertia out of the system, the net effect of that is that we see some problems developing wide scale and smaller scale around frequency and voltage. Now, in the western United States, in the Western Interconnection, where Southern California Edison is, we do have a fair amount of frequency support from the larger WEC, and our California ISO is responsible for managing frequency. The utility company is responsible for managing voltage, and that's where we're starting to see a lot of developing problems around voltage control. And the net effect of the introduction of a lot of this renewable energy isn't necessarily just voltage. It's that the timescales that we have as grid operators are starting to shrink as we see events developing, meaning the decisions we have to make in some cases are dropping below the traditional 4-second SCADA operation window where a human being could actually respond and react and make the right decision at the right time. This really motivates us to put a lot more modern equipment out there to help stabilize the grid and a lot more technology. Coupled with that, you see the introduction of distributed generation. So today, generation is dispatchable. You have a regional transmission operator or a utility company that's able to dispatch central generation and ramp it up and down as needed. Distributed generation, we don't have that opportunity often. Often the customer determines whether they're going to put power back into the grid or not, whether they're going to generate it. And even beyond that, not really the customer, it's the weather maybe determines whether that's going to come back into the grid. And the location of that distributed generation is not planned. It's not something that we as distribution planners or transmission planners really plan. It sort of goes in and interconnects with our grid at whatever customer point where they decide it's economically feasible and a good idea for them to buy and put this new energy technology in. So, it's the onus is on us to make sure the grid is reliable and help regulators and customers understand the impact of distributed generation. We do see part of that, management of distributed generation moving from sort of the standard tariff-based rates there are today to some level of signaling, whether it's a market-based signal, some sort of transactive energy type of management or reliability service that we offer to customers that have these types of equipment, or it's some sort of connection charge or management fee or something like that, where we make sure that we're able to sustain the utilities' assets and the reliability of the broader grid system using some sort of charge or feedback mechanism that helps the distributed generation equipment or storage equipment or DER equipment behave to contribute to the overall health of the system. And that's really what we're talking about, at that level. Lastly, that the system that we have today is fairly rigid, and we ask ourselves often the question, how do we make investments today in grid modernization that allow us the flexibility to accommodate the evolution of the utility and move as our architecture moves and needs to progress? We'll talk a little bit about, sort of our realization around that. So there's those sets of fundamental changes. It's a very interesting time to be in this industry and to be working on electric critical infrastructure because the changes that we're going to see, I think, over the next 10 to 15 years are more than we've seen in the last 100. So this analogy doesn't really hold up, but as I was saying, just like flight has these basic capabilities where the laws of physics kept the Wright brothers plane up in the air, and you compare that with a B-2 bomber that's inherently unstable, but it has a massive amount more capabilities. So we think the electric grid is going to move from this stability through physics, and don't worry, physics is not going away. It's definitely still a factor. But because we're going to see these inherently unstable types of technologies being integrated into the grid, we're going to have to augment the stability of the grid in order to maintain our current level of reliability, or even better, through technology. So for, I'd say, a number of years, I went to smart grid conferences starting in 2005 when it really picked up as sort of a buzzword. And what you would see routinely in presentations was guys like me from the utilities stand up and talk about their projects. Okay, we're going to have more synchro phasers, we're going to have smarter relays, we're going to have advanced metering infrastructure, But it really hasn't been until the last few years, partly because of a lot of the conversation in the IT world about big data and analytics and that sort of thing, that the conversation didn't turn to, well, how do we make this, the technology and the grid better, faster, more reliable, more secure, easier to manage? And those were the sorts of things we were asking ourselves in 2008 and 9. When we really started to take a hard look at all the projects that we had in flight. And we started looking at a lot of other industries, defense being one of them, and recognized that, we're sort of lining up on having communications and security that were application specific in silos. And so if you look at this slide here, let's see if I can get mouse going here. Here we go. If you look at the slide here, sort of the current state of utilities, and Edison might actually be in sort of evolution number 2 here, but you see these individual silos, right? An AMI system, a phaser system, a centralized remedial action system, a SCADA system. 2009, when a lot of us really started turning our attention to smart grid inside SCE, we recognized that security and communication looked like they were lining up to be different for every single silo. And we were going to spend hundreds of millions of dollars on proprietary security and proprietary communication layers and even proprietary computing technology. And we felt like, kind of the analogy for me would be our old mainframe billing system, right? Where we've had it for a long time and people have just stacked one thing on after another. There hasn't been a lot of architectural discipline, and it's so complicated and so fragile to tie different silos together and different functions together that everyone's afraid to touch it. And just at the point where we felt like grid operations and grid control systems were going to have to change to accommodate all this new technology and all these new policy objectives, we felt like we were about to make it overly complex. And we also felt like you really cannot meet or beat complexity with more complexity. You have to meet it with simplicity. So we started asking around, and we kind of turned to, your regular system integrators. And these are, kind of your big 4 or 5, I don't know how many there are now, but, traditional IT system integrators, and ask them what they thought their solution was. And they're like, we have the answer, enterprise service bus. This will meet all your needs. And so, so we drew the picture up and we went, well, the problem is we want to be able to have an AMI meter here in this silo talk directly to something in the substation or a volt-var controller. Not that that's the best idea in the world, but the idea is we want to make sure we get that information quickly to a volt-var controller in the substation. And you can do that, you can do that, but you have to go all the way back up to the back and across from the back office systems and then back down that silo. That's sort of where we are now. Don't get me wrong, I don't think you can skip this step. If you're in a siloed mode inside a utility now, I think you're probably going to have to put some sort of an ESB in the back in order to decrease the barrier to integration and get the information flowing between these systems without having an inordinately high cost when you integrate across silos. But we weren't satisfied with that. That does not meet the common services goals that we had talked about. So then we talked to a lot of large system integrators in defense. And we really felt like we had hit on a system architecture that we wanted, but the methods that they used to enforce that system architecture weren't correct for the utility industry. So, for example, a Boeing or a Lockheed Martin that's a large system integrator for the Navy or the Army or something like that, they would have an architecture where you could get access to common services in the back of anywhere in the system, actually, if you just used their API to develop your system. And when we were talking with these guys, we really didn't feel like, okay, we could enforce a GE or a Siemens or an ABB to use someone else's proprietary development kit to develop their own APIs. So even though we felt like the system architecture was roughly correct, it was not commercially viable to take that approach. So, and we really didn't have the ability. DoD will hire somebody for a $150 billion 10-year contract, and they can enforce whatever the standards are on the subcontractors. That's not the case in the utility industry. We're still, in our rate case filings, taking these one chunk, two chunks at a time, so you don't really have those big integrated projects. So moving to the last evolution, we did feel like, look, the private cloud architectures, even the public cloud architectures you're seeing today are correct. We need standards to hold them together, but you would accomplish the same thing. Any device can talk to any device can talk to any system, and they can access services like cybersecurity and communication from anywhere in that system. So we worked on this in Caltech. We published a paper in 2009 on this system of systems research that I think got a lot of feedback and felt like we were confident. So we knew what we needed to do, and felt like, well, in advanced technologies and in system engineering for the grid, what's the best high-level strategy to start working through that architecture and getting the resources together that we needed to approach these problems on our existing projects. So when we do work inside advanced technologies, inside architecture work inside my system engineering group, we don't just stick with the technology stuff, right? We talk to policymakers to help them understand what we're doing. We focus on kind of this value engineering thing where, okay, let's not gold plate everything. Let's use the best that modern technology has to offer to upgrade the grid, but at the same time, let's make sure we're doing it in a way that maintains affordability, reliability, and safety on the grid. Some of the other points on here, mitigating the risk of technology obsolescence, right? A lot of what you see with new technology are very fast cycle technologies. And utilities invest in technology that they think is going to last 30 or 40 years. By the way, we don't think that as much anymore. We at least want it to last 10 years at this point. So there, we're really looking for those architectures that help us evolve. How can we have legacy systems participate in a modern cybersecurity system, right? Those are the questions we need to answer. It just is not responsible to put some of these new capabilities out on the grid without the appropriate cybersecurity. I'm not even talking about compliance or NERC compliance. That's the least anyone could do. If you're going to put something out there like a centralized remedial action scheme system that controls the relays that connect the generator to the grid, you have to secure it with modern technology. The vulnerabilities are too high. It's too irresponsible to put it out there without more modern cybersecurity. So we felt like that in 2009, and we went shopping, and we didn't really find much. So I'll talk about the security, our kind of security stuff in a few slides here, but we decided to really zoom back up to the system of systems level and understand what are the policy drivers. And utilities are largely instruments of public policy. I mean, a lot of times we wish we could be a little bit more proactive. Sometimes we have regulatory constraints. Sometimes we have cultural constraints. But generally, we tend to be a reactive industry. So we looked at all of our policy drivers, and then we looked at all the capabilities we needed to enable to meet those drivers. And these are things like 33% renewables, zero net energy homes, electric vehicle penetration, reduction of carbon footprint, all those other types of things. And we came up with these capabilities, and then we started working on, okay, what are the systems, the communications, the field devices that we need in order to enable these capabilities, and how can we approach the design of all these capabilities as an entire system rather than a one-off. So we were able internally to sort of change our mindset on how we approach this. And the project teams that we had running these individual projects were a little resistant sometimes, but I think now that they understand that, you know, it's not going to cost us $150 million to secure all these different systems and programs. It's only going to cost us $40 or $50 million, which is still a lot of money. But you know, you have that savings. They were generally supportive. Just so we're, you know, I want to make sure everybody understands what we're really talking about inside SCE. So these are the smart grid projects we have underway. We have our CRAS project. We're putting out quite a few synchrophasers. We have 20 out there right now. We're probably going to move about 70 or so over the next couple of years. We have a new 61850 substation automation program where we're actually upgrading our system, our substations to 61850 and IP-connected communications. We have a lot of control system upgrades underway. They tend to be, you know, kind of arduous and expensive, but we're trying to put some sort of integration layer behind them so that we can get the value out of all the data those systems bring. I'm going to talk more about our common cybersecurity services. Obviously, we have a lot of smart meter data. That's our Smart Connect program. We have a myriad of NERC SIP projects as far as cross-domain type solutions. How do we make sure electronic security perimeters are maintained? How do we keep substations from inheriting the high-level designation and physical security requirements that a grid control center has when we connect them together through encrypted tunnels? Those are the types of things we're working on. We have a large project to upgrade most of our fiber optic communication network to an MPLS network. Edison's a little different than most utilities in that we own a telecommunication company which connects, where we lease fiber to connect Verizon and AT&T cell towers across our service territory. So most of our substations are fiber connected. You don't actually find that in a lot of utility companies. And then we have other cybersecurity projects around identity management, user access controls, sort of the normal stuff. So those are some of the smart grid things that we have underway. There are definitely other things in research and development that are also moving along, like transactive energy and microgrid projects and that sort of stuff. We decided, you know, it was great in 2008 and 2009 to run around to conferences and talk PowerPoint presentations about all our stuff to everyone. But the thing that concerned me and everyone else in the utility, particularly in grid operations, is we did not want to screw up the reliability of the grid with new technology. And so our concern was, well, how do we make sure we don't launch this new technology attack on the grid, right? Get stuff out there that operations doesn't know how to use or isn't really technically mature enough to be integrated with it. So we built a advanced technology smart grid lab. There's 8 labs. Basically, they represent the end-to-end grid. I'd say the sparkling jewel of that is the power system lab, which is our RTDS implementation. It runs a model of the Western grid down to the specific oscillations of most of the large generators out there. We continue to work on the model. All the other labs are tied into it. So we have sort of a set of grid control applications, distributed energy resources, substation automation, distribution, home area network lab, or we're going to change that, I think, to the connected grid devices lab or something like that. And then sort of for the garage of the future where we test EVs and electric vehicle service equipment. But they're all connected into this simulator, and that allows us to do hardware-in-the-loop testing and system-in-the-loop testing. So our new 61850 substation design, we can test the entire substation design in the context of how it would function in the Western grid. We can run thousands and tens of thousands of scenarios, failure scenarios, to see what the configurations on each of the individual relays should actually be. It's not till you really get your hands on the equipment and start, you can't really understand it, right? You're either in the marketing brochure land or you've got your hands on the equipment and you're understanding what its limitations are and you're able to actually really talk to the product engineers at the different companies on the problems that you're seeing and working together on how to resolve it. So the lab's been extremely valuable. If you're in Southern California, give me a call, and we'll see if we can arrange a tour for you guys. This lab's in Westminster, California. So back to thinking about security. So we had the lab, we had an architecture, we had a set of policies and objectives, we had an agreement across the company that we were going to approach the design fairly holistically. When we started talking about the goals of security, right, I think everybody bought off on the fact that some of these really advanced applications you didn't want to put out there without security. So right away, we talked about, well, you really do want to secure the data and the information coming from the sensors. The goal is to securely get the information to the right people in the right place at the right time so the right decision can be made. And sometimes that's machine to machine, sometimes that's through a grid control center with a bunch of operators. But that was our focus. And like I said, we had shopped around quite a bit in the industry for solutions and talked to our individual vendors, and we found some e-commerce grade sort of PKI type solutions which were okay, but we didn't feel like they were fast enough for a lot of our applications. They would serve maybe some things in the distribution network, but they weren't going to support what we needed to do in protection because they were a little bit too slow. We talked to a lot of telecom, we talked to defense, we talked to a lot of computing and internet type of companies kind of looking around for what they were doing for cybersecurity. And we really hit upon the fact that we think the utility industry is sort of at the beginning of what the Department of Defense went through 10 plus years ago. About 10 years ago, and maybe longer, maybe more like 15 now, the DoD decided they would move to this network-centric warfare paradigm. And kind of they worked on the global information grid and a way to connect all their forces and different vendors together across the globe. And we felt like that's really where we're heading from a networked utility operation. We really did not want to suffer vendor lock-in, right? Like in Europe, 61850 substations are typically supplied by one manufacturer. You don't have multiple brands of relays. So ABB will build a whole substation for, Electricity de France or something like that. And then for another German company, Siemens will build one, but you don't have, it's all one package. And our experience with vendor lock-in has always been, as soon as we agree that one manufacturer is going to satisfy all of their requirements, somehow the next upgrade is always $20 million. And so you're just held hostage by that. And we wanted to make sure that we didn't erode all the value of everything that we talked about and tried to do by missing that point, that once you're locked into one vendor, you don't have any flexibility, and you're going to move at the pace the vendor wants to move at, not at the pace you need to move at. So it was really important for us to kind of come up with this design where we could support multiple applications. So we started, we found a defense contractor that was willing to work with us. Well, actually, there's 4 or 5 defense contractors that are licensed to do or certified to do Type 1 through Type 3 devices for the NSA. We talked to each one of them. Most of them wanted $500,000 just to send us a proposal. So we found a smaller one actually that was willing to help us with this, and started working with them under our phaser measurement project 5 years ago, and recognized that, well, we want to satisfy all those smart grid projects that were on that list. So we made it its own project, its own capital project. And we really wanted to use these there's some buzzwords in here, right? So military grade technology is kind of a buzzword. We're not using, classified crypto algorithms, just to be clear. We have the ability, the architecture has the ability to accommodate that in the future if we ever got into a situation where we felt like we needed to go there. But really I'm talking about more the methods and the architecture that defense has used. Those are the types of things that we're transferring into our solution. We decided we really, we're on this merry-go-round where we're spending $10 million a year with 100 people doing paperwork for NERC version 3, and we could see the company spending $100 million trying to do NERC version 5 and meeting just the minimum set of requirements necessary to comply. And whether that's an avoidance strategy where everyone uses serial connections instead of IP to comply and just spends $10 million a year on paperwork, which is kind of a waste, or whether that's we're going to do some technology things but just do the minimum set of requirements necessary to comply, we really felt like we wanted to design a system that would carry us through the evolution of NERC standards. And we felt like if we could project the direction of where NERC is going to go or where they are going, it feels like they're headed towards federal information protection standards. It kind of makes sense, but it looks like it's going to be a long time in coming. So we decided we would just build a system that met a lot of those NIST standards, DHS and FIPS standards, and we would use that system in order to put the security controls and establish the ESPs and EAPs in NERC parlance necessary to comply not just with version 5, but beyond that, version 6. We'd be able to roll it out as we rolled out and replaced all the serial connections in our network with IP connections. We wanted it to be really scalable and a fairly dynamic and reactive security system. Basically a policy, when I say dynamic or flexible, it's a policy-based solution. So we didn't want to be hard-coding everything in and having to do firmware upgrades every time we sensed somebody was attacking us. We wanted to have some tools where we could detect and respond very quickly. So sort of those basic resiliency engineering sort of characteristics, right? Let's detect the event very quickly. Let's survive and shorten the length of the event if we can. Let's recover from the event as fast as possible back to normal operations. So that kind of resiliency approach is really what we took to. And I've already talked about the multi-vendor adoption path. So at the highest level, the Common Cybersecurity Services has a lot of the things that any security system has it in. It has authentication and authorization and accounting. It has key management's not called out very well in here, but it has a fairly robust key management system baked into it. It's also got some things that are a little bit more interesting in it that I think are unique. So this idea of quality of trust, right? A set of policies that will actually describe whether a device, so there's an integrity management authority at the top of the system that will look at the quality of trust, meaning the conformance to policy of any individual device. And for any device that has a security association with the other device, the integrity management authority will tell those other devices whether the data coming from it is trusted, right, green, suspect, yellow, untrusted, red. We'll talk through some of that stuff. The other thing that I think is really interesting about our implementation of CCS is this Bill of Health set of policies. So Bill of Health is sort of under that integrity check, and basically it's a set of policies that describe what the behavior of the device should be in the context of the overall system. Sometime in the future I have dreams maybe of using this as a platform for distributed control, but right now all it means is we can have an upper and lower control limit on voltage, and if a device starts behaving really badly, we'll be able to send an alert and a notification both on the quality of trust on that device and alarms to operators to say, hey, there's something going on wrong here. So that's the idea with that Bill of Health. And then we put a lot of work into the GUI. I think, with AMI systems, even though we had baked some security in, we had the scrolling list of events coming from 5 million meters. And first early days of operations, every time somebody would plug a meter in, we'd get a tamper event. And so, we would just see lists and lists every day. We were putting in, 12, 15,000 meters as we installed every day. And the operators, there was so much information that nothing was actionable, right? So the idea was we were really going to try and work on those filters and the visualization so a security operator could understand. Make no mistake about it, the system that we're working on, you can't run in some security operations center off in some IT building. These guys have to sit right next to the grid control operators. There's no way that they can understand what it means to see, something go red out on the screen without talking to the grid operator. Oh, what's going on at this substation? So we really do need that joint operations center approach with this sort of stuff. So some of the technical aspects of this, today I think if you look at that, the routing equipment sort of in the middle labeled PE, you would see today's utility electronic security perimeters just kind of being around the router, and then you'd have devices at the edge without any security on them. So we've done a couple of things. There's a set of central CCS services, Integrity Management Authority, Security Operations Console, Audit Services, Key Management, that sort of stuff. And then there's clients out in the field, CCS clients that run. There's different form factors, right? Software and hardware based form factors for these clients that run actually on the devices. So you really do have that end-to-end security. And then we've cut the communications into 3 different control planes, and each control plane has its own set of keys. So there's a control plane for the data, control plane for the network, and control plane for security communications. So if somebody gets into the network layer, then they have to break through the security to get into the security layer or up to the data layer. So this is helpful. That's one of the methods that we got out of defense, and one of the reasons we're putting in this MPLS core network is to manage those control planes. The other thing is we have these community of interests. So a lot of times the executive, 4 or 5 years ago when I was kind of pitching this to our executives, they'd be like, "Let me get this straight. You want to gold plate the entire grid with advanced military grade security?" And I'd be like, "No, that's not what we're talking about. We don't need the same policy and the same security on a relay that connects a generator to the electric grid as we do on an AMI meter, for example. But we could use the same architecture. We could use the same management software. We could use communications platforms, sort of layered underneath, bridged together. And so we have this idea of key groups. So policies are assigned to key groups. When a device joins a key group, then it inherits the policies for that key group. So if it's part of the relays that support a centralized remedial action scheme and a bulk electric substation, has a certain set of policies. And if it's in the distribution network with a bunch of other remote fault indicators, then that has a lower grade of policies. When there's a security association between 2 devices in different key groups, the device that is at the lower trust level actually inherits the policies of the higher one, so it can communicate for that period of time. What this allows you to do is you can do a couple of things. First off, besides being able to have these separate key groups, you're also able to redefine key groups dynamically if you want to change the trust boundaries across the network, and that is super helpful, particularly if you're, this might be one of the ways that you could respond to attack. Each device has a client on it, and there's the status, it has a heartbeat, right? All these things are configurable and policy-based. The bill of health, which I talked about, and there's the quality of trust as well. And then your regular RBOC sort of stuff with certificates. But you can have devices with different policies on it, and you'll see the same thing. And you'll have to click into, on the screen, on the UI, you'll have to sort of click into each one to see what the policies are and what the devices are. So this is a shot of the screen, and there's a couple of different interesting views on here. We can show things geographically. You can look at an individual device and see the data suspect or the certificates are expired, and then the operator can either refresh them. We're sort of working on the higher level automated types of response. Viasat is the company that's helping us with this, and we won a DOE grant to do sort of a cyber intrusion automated response type of project on top of the CCS platform, so we're currently working on that now. But you get a sense of what the operational grid security posture is. But again, some of our challenges are you have to have security operators that understand enough about the grid to understand what they're looking at and what the impact might be, and enough about cybersecurity so that they understand what the threat is and what it means when something turns red or yellow. And so if they're smart enough to understand all that, they're not really going to be content with staring at the screen for 8 hours a day. So we're really trying to figure out, so the challenge we had on AMI, right, was we had kind of the best communications engineer in the whole company. We were working together on AMI, and when it came time to operations, instead of John coming over to work with me on smart grid stuff, we had to promote him to be the manager of the AMI operations center because there was nobody else who understood anything. And so that's some of the challenges we're having here. I don't necessarily want my system engineers to be moving into productions and operations support roles because we can't find anyone who can do this stuff. So this is our current challenge right now. We're sort of working on it. So far, what's worked is we hire some folks out of school, and they're pretty happy for like a year. And then we really have to move them on to engineering and design. And so these are the types of things that operationally we're somewhat challenged for. So we're really looking for the right people to look at this stuff. We're kind of exploring, people who worked in the Army and these types of operations centers maybe would be the right fit for this sort of stuff long term. So where are we? We've been in production since about mid-2013 in one substation and with a bunch of radios. We don't have a broad deployment of CCS yet, but it is stable and operating. Right now we're sort of talking with a lot of federal agencies and our utility peers, about the solution. I think whenever I go to Washington, D.C., and I introduce myself as a utility guy, somebody says, well, why is your industry so slow? Why aren't you doing anything about cybersecurity? And I'm able to talk to them about this stuff, which is good. But this stuff is a little bit under the radar. GE has decided to adopt CCS specifications across their entire company under a Cyber Sentinel program. And this is really good news, not just for the utility industry, but healthcare, transportation, and some of the other industries they have will also be leveraging this. We're in talks with a whole bunch of other vendors as well. And lastly, so we do have CCS. There's software. I'm kind of hoping that it gets rebranded as something else. But the common cybersecurity services specifications, build-to specifications for the client and the system are really the set of specs that we want to publish out to a lot of vendors, to the academic community to get feedback on their build-to specifications. And typically what I would have done in the past is publish this out to a standards group and see if they wanted to use it or adopt large portions of the specification as the standard. The utility industry is not, frankly, very mature in its approach to cybersecurity, and so they're disconcerted mostly by the idea that we would freely publish security specifications, even though security is not really maintained by keeping secrets. It's more about the strength of the algorithms and your architecture. Having said that, I'm not able to publish them openly, but we will provide the specifications to anybody that asks under non-disclosure agreement, with a few exceptions. But that's where we are. Okay, I think I've got about 15 minutes or so left for questions, so thanks very much.
So I'll start us off, Jeff. Thanks for the presentation. One of the things I noticed in your early tenets in slide, I think 3 or 4, where you were talking about what you need to, that slide, the holistic approach to serve customers better. So kind of cross-cutting through there is the notion of resiliency, but it's not explicitly called out. Can you talk to that and why that is?
Right. I think it's, so system engineers like me love to talk about resiliency. Utilities talk about reliability. And there is a difference, and it's a little bit nuanced. So we felt like a couple of things. The term resiliency is sort of a buzzword like architecture unless you're precise about, what you're talking about, like I was, right? Shorten the event, all the kind of regular resiliency stuff. We found that the resiliency doesn't get a lot of traction inside utility companies with kind of traditional operations folks. They see it as that buzzword. It's not until you have the next level down conversation that they really get it. So make no mistake about it, this is all about resiliency, right? You're absolutely right, and that's absolutely the path we're on. But we tend not to call it out too much because, I don't know, maybe a bunch of consultants have picked up the word and it's kind of a buzzword like big data is now, right? But I think as we mature in our understanding, we'll start to see that in our language a lot more. Thanks.
Hi. So Carl Gunter. I was wondering about the quality of trust concept. You mentioned a classification into green, yellow, red. I was wondering, is that the granularity you use? And also, what do you use to calculate what gets me from green to yellow? So
right.
How does it work?
So right now, it's completely subjective. So green is you're compliant with all the policies. Yellow is an interpretation of the data, all the inputs and outputs that we see that would leave us to believe that there's something about the device that we want to make sure the security operator knows before he takes some action. Red is either we're not, what's interesting is there's technical things that can go wrong right now, and this is the maturity of the software, which is getting a lot better. But there's things like, okay, if the DDS service is not running, everything's going to be red. That's not actually what red should mean. What red should mean is the device is actually in violation of some of the policies that we set, and the data should not be trusted. Now, what's important to understand is, unlike the IT business where it's confidentiality, integrity, availability in that order, in the utility business, it's availability, integrity, and confidentiality. So even if something's red and the data is untrusted, we still may take some level of action if we see low risk in actually pursuing that. So if you look at the maturity of this, it's immature. So in an immature technology like this, what you're going to see is engineers making subjective decisions on where you cross the line between red, yellow, and green. In the future, we would love to see some studies, some mathematical calculations on, if you look at the upper and lower control limits on how this device is behaving, or you have signatures out there, or you have specification-based sort of things going on that leads you to believe that something is going wrong from a security standpoint, more sophisticated sort of processing in the background would help guide your movement between those two, but we're not there yet. So we've got the base technology platform in place, but what we don't have is the more sophisticated policy enforcement type of a design in place yet.
From what you
Great
said,
question.
an interesting classification might be that green would be sort of verified security, yellow would be unverified to some degree, but no evidence that there's a problem, and then red would be some evidence of a problem. So that might be a possible semantics.
Yeah, that would be that would probably be more clear than where we are now. So I definitely appreciate that. Thank you.
Okay. Thank you. Very informative talk in general. I have two questions, and they're completely unrelated. One of them is that it seems like a really great approach. On the other hand, does it map well to CIP's compliance?
Right. So CCS is first a cybersecurity system, and second, it is a compliance system. So we're building the compliance controls in to CCS, but our first thought was, let's make sure the grid is secured against attack. So if you look at how what we're having to do after NERC CIP 5 came out and really got published and got a lot of traction last summer, we had to go back and take new requirements and upgrade the system so we could establish electronic security perimeters the way that the specification called out. We had the logging capabilities and the reporting capabilities that were called out. We could have, what we sort of shot for is each device could be its own ESP or EAP, but what we found out very quickly is the documentation burden under audit of making every device its own contained ESP and EAP was probably going to be too high. So then we started moving to the gateway sort of scenario where we might proxy in front of a bunch of other devices with that electronic security perimeter. So it's a little awkward that we had to, in some cases, I feel like we're eroding the actual cybersecurity that CCS could offer in order to comply with the NERC CIP standards.
Interesting observation. My other question is, how do you generally handle connection to third-party systems?
So right now, I think like most utilities do, we have a kind of a jump box sort of approach. We're working, if we look at our Irvine Smart Grid demonstration project that we did with the DOE, we have a couple of different ways to do it. So we actually are, for some of the battery control, going through the third party's cloud service and sort of a B2B or business to device using their cloud service. We're okay with that for beyond the meter applications. So if it's something in a customer's garage or on their rooftop or even some larger commercial generation of some sort of battery storage, we're okay with that. If it's something on the grid, right, we'll require them to come through a jump box. It's sort of this, think of it, there has to be explicit authorization with a human operator saying, okay, now you're allowed to connect to the system, and here's all the rules around that. That's typical, I think. We are, in order to transverse across different trust levels in the organization, we actually, and maintain those ESP boundaries between the grid control and the enterprise and that sort of stuff. Like I said during the talk, we're looking at cross-domain solutions and even some high assurance guard type of technologies, again, tech transfer from defense, to maintain those boundaries. So I'm not sure I answered your question, but all right, thanks.
Hey Jeff, thanks for the interesting talk.
Sure.
Very exciting and refreshing to see utility putting security first and compliance second. And I think NERC will be happy too because that's what they want anyway.
We've had some positive responses, not necessarily from the audit group, because I think they're concerned about, okay, now we have to understand this. But more from the NERC executives are very interested in this approach.
I think that's what I don't know how audits work, but I know the people who are actually drafting these things would like it because that's what they want everybody to be doing. It's just that they can't prescribe everything in a standard.
Well, and I may be a little critical sometimes of the NERC CIP standards, but there are realities about the industry and where we are that drive some of those requirements that we have to, accommodate right now. So anyway.
So I had one question on something on your slide that said cyber physical indicators, and I was wondering if you could sort of elaborate on what those meant. In the list of, maybe I misread it, the blue boxes, one below the other, I think the CCS, when we're talking about CCS. Yeah, that one.
Yeah.
So you had cyber and physical alerts. Okay.
So for us, that's really the idea of if you have an alert from your cyber side where something's happening locally on the device, somebody tried and changed the password 5 times and it didn't work, and you correlate with your work management system, nobody's supposed to be out there. Can you turn on the video camera that's pointed to that device? Can you access the physical badge system and kind of look out there and see what the situation is and understand whether it's a threat or whether somebody's in there, at the wrong time and got the wrong substation and is making a mistake? Or those are the sorts of things we're talking about.
So an interesting thing, and I don't know if you're going that far now, but so you already have this quality of trust metrics. When something is not right, you call it, turn it yellow or red. But so I'm asking this because we have a project on this, in this direction. I wanted to see if you see this as something near term or medium term or long term from your perspective, is to look at your cyber network with all of this visibility and security built into it, and now look and then say that for contingency analysis, we do them based on random failure model right now, or accidental failure model.
Right.
There is some thought about dealing with cybersecurity induced failures and dealing with those contingencies. But now that you have this kind of well-established security framework here, you could actually take advantage of the information you're getting and then only focus on stuff that you think are probably
I think that makes a lot of sense, that sort of idea that if you could estimate the state. We had some conversations earlier today about state estimation of cybersecurity. I think that is kind of a medium-term thing.
Okay.
It may be nearer term for like an SCE, but for sort of commercialization and broad industry adoption, medium term. And to be honest with you, with all this stuff, the adoption will generally be kind of slow and methodical in the utility industry unless there's an event. And if there's a large event that gets a lot of traction, you saw this post-Stuxnet sort of thing, then you're going to see a lot of action on the policy front, which will motivate a lot of utilities to kind of move faster. And you're seeing a little bit more and more of that acceleration, right?
Yeah,
So I think the research is valuable.
Perfect. So maybe we can talk, and let's not hope for an event, but slow adoption is good for us, and we can talk about it. Yeah.
Absolutely. Thank you.
Okay. I'm actually a placeholder for the online questions.
Okay.
We have 2 questions from online. What do you see as big security needs that your security architecture and vendors, largely recycling from other industries, are not addressing, or perhaps what your architecture is covering but you'd like much more depth? Any low-hanging fruit in those regards?
Yeah. I still feel like if you look at security analytics and sort of this idea that we need to be able to evaluate traffic and tie different streams of information coming from different devices together in order to understand what our security posture is, that would be great. I think security standards are, pretty high level, but they don't go far enough to ensure interoperability, which is, one of the things we put this together for. Our hope is that it will be broadly adopted, but if it's not, then it's going to be a patchwork. I think some of the challenges are so we're all interconnected at the power level, and we all have different control systems and different ways of managing, but at the same time, if we could share a common operating picture of what our security posture is at any given time, not with just the utilities that are next to us, but even with civil authorities that are in our territory and military bases and stuff like that, that would also be something that would be very valuable. Now, I wouldn't expect the vendor community to go do that first. That's sort of a more mature thing. I think the analytics, once we get this information, what do we do with it question, is probably the short-term sort of kind of burning platform.
Okay. And then you mentioned the security operators and power operators working side by side. Are there other things that you've learned from using CCS in practice, particular problems that arise, frequent issues to deal with?
Yeah, so logging is awesome, right? But if you have too much information coming to you, right? If a security operator gets 150,000 alerts, and this is kind of the early days of CCS as we were just turning it on before the kind of the filtering, then the information's not actionable. So even though you have this robust capability to push all these alarms and alert off, it does not give you actionable information and actually makes the system less valuable. So that was kind of one lesson we learned, and the vendors been very responsive in doing this. The other thing is the integration of this it tends to be fairly difficult without virtualization. So if you have a virtual machine and you put with virtual NICs on north and southbound side, and you put CCS in the middle on a machine, whether it's Linux or Windows, pretty clean. The existing vendor can do their own, application the way they've always done it. It's not exactly secure within the box, compared to natively running CCS, but the ease of integration is more. If you try and bake this stuff directly into the applications, you get much higher value from CCS, from all the monitoring, but the cost is more and the time and energy is more. So the hope is that an ecosystem evolves that it's actually able to start investing in this without our company or another utility company paying for every single nickel of integration cost.
Okay, so I think we're basically at the end of our time. Extremely informative talk, Jeff. I think I express gratitude on everybody's behalf, and thank you for coming out. And once more, let's thank the speaker.
Thank you.